everyone. So welcome to our first Quantum at Sun seminar for this year. So our first talk is given by Dean Brand, so I'm sure pretty much everybody here is familiar with Dean. So his talk will be on Markovian noise modeling and parameter extraction framework for quantum devices. So maybe I can just read out a short part of your biography. So as I'm sure most of us know here, so Dean's a second-year PhD student in the quantum research group at Stellenbosch University. His current research focuses on the intersection of quantum computing and neuromorphic computing to find an optimum hybridization of these technologies. His research interests evolved to include machine learning and quantum algorithms, which are central to the idea and aims of neuromorphic quantum computing, especially for applications such as artificial intelligence and deep learning. So yes, thanks Dean in advance for volunteering to give this talk, and so yeah, over to you.
Hi everyone, welcome to this presentation. Just sharing my screen. So it's nice to finally be talking about this work and sharing it after quite a while in trying to get it published, but luckily it was finally published on Tuesday this week. So I'd like to give a nice run through of what exactly the research was and what we did, without really needing to go into the nitty-gritty details of it all. So the paper that I'm presenting on is called Markovian Noise Modeling and Parameter Extraction Framework for Quantum Devices, because it's a bit of a two-part research. It started with looking more at the ability of us to apply a Markovian noise model to quantum computers, and then we saw that we could morph it into a very nice, a very convenient parameter extraction framework and almost a quantum process tomography algorithm. So the motivation behind all this was pretty much three main reasons, and that we saw there was a lot of conflicting claims in the literature about the behavior of quantum computers, specifically superconducting quantum computers, but more specifically the IBM Quantum computers. We saw that they modeled all of their systems and examples, and everything that they showed was almost with the assumption that their computers behaved according to a Markovian noise model. And I'll get to a deeper definition of Markovian or non-Markovian just now, but for right now, it just means that the Markovian one is much, much easier to model and a much nicer system environment. But we also saw there were a lot of papers being published around the time that basically had the assumption that these devices were already non-Markovian and then proposed frameworks on how to deal with that once they're already non-Markovian. So we wanted to see, well, which one is which, or what's really going on. And we also saw that when trying to model any open quantum system specifically, or any quantum simulation on these quantum computers that was dependent on the actual hardware parameters of the quantum computers, like the frequencies or the temperature or the relaxation times, the only way to really know what those parameters were through a list that the backend host IBM would publish. Basically once every hour they give a set of calibration data, but those would vary quite regularly, and then if you got caught at the end of a calibration cycle, you wouldn't really know how reliable those parameters were. So you wanted a way of extracting all of those all at once. And on top of that, we know that when they tried to give these data, they would extract it sort of one by one. They would do one experiment to calculate T1 relaxation time. They would do another experiment to get the temperature, which they controlled. They would do each parameters kind of individually in a different way, but that wouldn't account for if they influenced each other in any way. And they also were very careful in avoiding addressing the idea of what happens to neighboring qubits. Like if one qubit goes from an excited state and relaxes, what happens to its neighbors. Is the energy possibly kicked into its neighbor or not? Because in all of the examples and all of the calibration data that IBM published, they were very careful to never use neighboring qubits, but only qubits kind of far apart from each other, and being a little bit ambiguous as to why. So we wanted to look a bit deeper into what happens in those circumstances. So I want to give first a little bit of an introduction into the IBM quantum qubits, and then go into the open quantum systems, and then see how we mix them in this paper. So the IBM devices use superconducting transmon qubits in various different connection topologies. Like at the bottom, there's a map for just the linear device, where there's only those other connected ones, but they're much more complex ones with the much bigger devices now. And they claim that the qubits are modeled by a very simple Duffing oscillator Hamiltonian with mostly just these three terms, F left alone, without any driving force or any more complex dynamics. But just on its own, this is a very simple model for the Hamiltonians for each qubit, where this is a 2-qubit system where it considers the frequency and the state of the first qubit and the second qubit, and then the coupling constant between them, or how they then communicate with each other. But we also noticed that this might be an oversimplification, so we wanted to make the model a bit more general and see if there is something bigger going on, if it's not just a direct connection between the two qubits, but if it is connecting across different axes. And yeah, when looking at the calibration data, they would notice that they just give this one table about once an hour that gives you the calibration data of the qubits, mostly the T1 or the T2 times, the frequencies. They don't even mention the temperature. They only vaguely say that they dilution fridges are kept at around 15 millikelvin, but there's no way of really seeing that directly. Except there is then a way through actual open quantum systems that we can extract that through the average photon emission for when a qubit relaxes. So yes.
Go to the previous slide. What is this J?
This J is a coupling constant between the two qubits. Yes, for how they can then communicate to each other or link, or how you entangle two qubits, how you have a 2-qubit system. They have to link it somewhere. It's through this coupling constant.
Sometimes we use this parameter, this number, but here is a matrix.
Yes, in the simplified model, it is just a number, and then the plus and minus operators for how they can actually communicate. But we thought it might not just be the simple case where it's just the two qubits communicating directly to one another, but that there might be other degrees of freedom that they might be connecting to, which is why we wanted to look at the full matrix.
Is a simplified version of this.
Yes.
Okay.
And so that leads me then to the open quantum systems model that we wanted to look at, because we've also seen a lot of literature talking about how quantum computers are a very good test bed for looking at open quantum systems dynamics, because each qubit is an open quantum system. And the Markovian model that I mentioned earlier is the simplified memoryless model, which basically just means that if a qubit is in an excited state and it relaxes, then the energy that leaves the system stays out of the system. It doesn't come back. Because in a more complicated or non-Markovian system, where the energy might go to another qubit and then come back, or that energy might still stay in the system, it will make the future dynamics much, much harder to predict. But in this simplified model, then it's a much easier way of looking at all the energy that goes out just stays out. And the way that we've modeled that is by looking at a Markovian master equation, specifically the GKSL master equation, which is a nice simple model that we could look at as a first case and have then the very simple definition of if it fits this model perfectly, then it's Markovian, and anything else is non-Markovian, because there are more complicated definitions that you can make, but that's what we went with in this research. So in this equation specifically, we look at a few things. Firstly is the unitary evolution that the system would go through in an isolated system. Then this gamma factor is a decay constant for it controls how quickly the system decays into either decoherence or just back to the ground state, depending on the path that it goes through. This N factor is average photon emission for how much energy is then being kicked off in the form of photons, which is directly correlated then to its the qubit temperature. And the yeah, I think that's mostly it. The rest is just the Pauli sigma operators and the rho for the quantum system. So the two processes that these qubits can go through to decay are basically the relaxation and the decoherence. And the relaxation is a very simple model where if a qubit is in an excited state or the one state, then it just decays back to the zero state. And that's a very basic model of it decaying. And the decoherence is if it is in, or it's sometimes called pure dephasing or transverse relaxation. The terms get a bit fuzzy, and depending on which field, they have different preferences for what to call it. But it is essentially the qubit being put into an equal superposition of states, into a plus state, for example, and decohering into an equal probability of all states. So that basically means that you can't extract any information of it because there's a full 50-50 probability for any state being measured. And so this framework that we wanted to construct was basically taking the pair of ground state qubits, or a triplet of ground state qubits, or a single ground state qubit, and putting it through either a T1, T2, or T2 star circuit, which the T1 is the relaxation, where it's a very simple excitation and decay, and the T2 and T2 star are two variations of the decoherence. And the terminology comes actually from nuclear magnetic resonance, so it's also a little bit fuzzy in its definitions and translations, but how we define it here is just with the more broad model, which is also, these are the times that the IBM quantum computers claim as their back-end times that they quote as a T1 and T2 characteristic time of the qubits, because these characteristic times are like an inverse decay rate. And then the system goes through these, and then we use the calibration parameters to solve a Markovian master equation and see what it would predict. We see if it is the same model, if it's Markovian, if it's not, if it gives a completely different form, then we know. But if it is Markovian, then we can take the two solutions of the actual experimental data and the calculated solution and tweak the parameters of the temperature, frequency, coupling constant, all of that, to then get those models to fit. And then once they do fit through a very simple optimization gradient descent process, then we have a new set of parameters, which are the actual set of parameters, not the previously calibrated, quoted by IBM ones, but a true set based on the actual system that you're using, which is much, much more accurate.
Which is under the assumption that it's Markovian.
Yes, but as we saw from all of our stuff, which I'll show shortly, it was, for these models at least, a pretty much perfect Markovian model that would fit them. We didn't see any weird differences or any weird bumps in the graph, but it fit the model perfectly, but the parameters were slightly off, so the graphs were slightly offset. But by tweaking the parameters, we could get them to match perfectly, which is how we need them.
So it wasn't Markovian.
Yeah, it wouldn't be able to fit because it's a completely different way of describing the system. So just to go through the quantum circuits that we use to create these benchmarks, this is a very simple T1 circuit, which is, for 2 qubits, it starts in the ground state, it gets flipped up into excited state, and then it's left to do nothing for a set period of time, which lets it go through that relaxation phase. And with a quantum computer, obviously, you can't watch it decay the whole time. You can only take measurements at certain times, because then it collapses the system and gives you your computational basis. So with this circuit, then we're able to look at 1 microsecond, 2 microseconds, 3 microseconds, and see how that curve then gradually decays. And this circuit is very simple. It can be done for 1 qubit, it's the exact same thing. N qubits, it's the exact same thing, just copied, just to see then if neighboring qubits would influence each other at all, which they shouldn't, but this is a way to then check.
Is that hard to implement on IBM, like a delay operation?
It was very frustrating to implement, just because the default version that IBM has is a very weird setup, where to create a delay time and tell a qubit to do nothing for, say, 50 microseconds, they don't just say do nothing for 50 microseconds. They put it where they put an identity gate and barriers for however many repetitions of that you need to, until it fills that time.
So you need to calculate how long there stays.
But then when you try and transpile it, then I'd see every time that my RAM would jump to 400 gigabytes and then it would crash, because it can't transpile however many hundreds of identity gates in a row like that, instead of just a very simple instruction of just do nothing for this amount of time. So I had to kind of remake that out of the, instead of using the Qiskit built-in ones. But other than that, with the delay gates, it's very simple, and then it's just the Qiskit. So it's a very, very simple circuit, but a weird little factor in the actual Qiskit creation. It could be, maybe, I don't know. I don't want to make them seem too sinister with this, but that could be. But now I've given away their secrets. So the T2 circuit is a bit more involved, but it essentially involves exciting the ground state into a plus state with a half pi y rotation, so that's in the superposition state. It's left to decay and relax and basically spread out on a block sphere, and then flipped a full 180 with a y gate, so that's on the other side, and that refocuses it. Basically, it goes into much deeper stuff of dynamic decoupling and bang circuits and everything. It's a bit more involved, but for the sake of simplicity, it's then refocuses it there and then flips it back to the original state. And then throughout all of that, you see how much the state has decayed through that full, or decohered through that full process. And a T2 star is a slight variation on that, but a similar idea, where it uses instead a Hadamard gate to put it into an equal superposition. It's left to decohere, and then a Hadamard gate to take it back. So it goes a full circle back to the ground state, but then almost looking at what does it lose while it goes through that process. And yes, so this is basically just saying that we can do it for 1 qubit or 2 qubits or however many qubits you want. They're not dependent on each other. There's no 2 qubit gates or CNOT or anything like that. But it's just to see the scale and if there's any influence of neighboring qubits. And then we found a very nice benefit to using this rather than trying to do a full quantum process tomography, but I'll talk about that a little later. So for the experimental data, you can see here that in a very, very simple single qubit T1 time, then looking at the pink dots, is in the excited state and goes through a very simple exponential decay into the ground state. And this is how IBM modeled their T1 extraction time. They basically do this and just fit a very simple exponential curve to it and then find the parameter by which it decays. But that ignores a lot of other things. Like it doesn't look at the frequencies or the coupling constants between anything else. It doesn't look at the temperature, the photon emission. It just fits an exponential curve to this, which it can kind of get away with, but we wanted to look a bit deeper.
This model as like a two-dimensional system in the third one bar.
Yes. Yeah, they make everything as simplified as possible to get the data that they need, which they can get away with, but we wanted to look at a deeper thing if there's anything that they're ignoring that might be important, but they can get away with it because we show that it is a safe bet. And yeah, the same with the T2 time, where you can see they don't both decohere to the ground state, but they decohere to they both being in a 50-50 middle state, which you can't extract any information from because you don't know even which was which. The T2 star has a bit more interesting dynamics. It's a bit of a damped oscillator, but also usually quite easy to model. This little bump here we didn't take it as a sign that it's non-Markovian, but rather just the fact that for each of these, you have to run, I think we did 75 was the maximum, 75 circuits in a row on 75 reset states, that it's not always going to be the exact same thing that you're looking at, but the next closest thing. So this we saw is just a relic of the experimental data that we saw in any of the calculations that we did. This is just the nicest looking presentable graph, but it does work nicely. This isn't just something that we swept under a rug. And for the numerical solutions, it was effectively taking that GKSL master equation that I spoke about and integrating that using SciPy and JAX and a few other tricks to try and make it reasonably quick. But then you could take any ansatz or any initial parameters, you could set them all to 0 and solve it with that and then try and iterate it, or any other estimate of what you think the parameters might be. But we thought, okay, the best case would probably be taking the actual calibration parameters that they use each time and that you can access quite easily through Qiskit, and then using those initial parameters as your ansatz for the integration, and then ansatz as in that's before we get to the iteration of the optimization loop. That's the first best case. So just to see if the models fits at all, if it is Markovian or if it's not at all Markovian, then to look at the experimental data overlaid with a solution of the GKS master equation and see, are they smooth together, are they not, are there weird bumps of system being re-excited from energy coming back in, which would mean it's non-Markovian, just to give a first look. And what we saw when we did optimize it was that it fits pretty perfectly. So we could see that we're pretty sure that this is a very good Markovian system, that there's nothing weird going on, under the limitation of having to use the IBM Quantum experience of sitting in a queue and putting 75 circuits in a row and hoping that the queue doesn't get interrupted and you only get half of them done and the other half later or something, that there might be weird fluctuations. But yeah, for as best as we could get using the IBM Quantum computers, this showed very, very promising results. And that was just for the simple case, but even then for the T2 time, with a slightly more involved quantum circuit, it gave also very, very good results. Even for this one, where it was one qubit went through the T2 star sequence, where it was rotated with a Hadamard gate into a plus state and then left it to decay and then rotated back, and its neighbor going through a very simple exponential decay T1 process and seeing if that in any way affects each other. And we can see that it doesn't. We can see that the GKS master equation maps it pretty much perfectly, which was very surprising and satisfying and a nice result to see.
Was this after you had already done the parameter like optimization? So that it was
Yes.
optimal?
I don't think I included them in this presentation, but in the paper that I include that, you'll see, like in this, for example, that the lines are the same shape and the same smoothness, but just slightly shifted off just because of a parameter tweaking. But yeah, the optimized results, then they fit perfectly as they should.
So what is the plug you just the parameters of place library for you take it to the loss equations and like then put it on the top, was also very old.
It's just slightly shifted, but the shape of the curves looks exactly the same. I think there is one graph that I have later in the presentation that you'll see of the unoptimized and the optimized curve, and just to see the improvement that it made. Because yeah, yes, when I talk about the parameter extraction, we found that this was a very convenient way to then do the very simple optimization loop and then get the perfect set of parameters that you're really looking for, and then say, okay, I can actually reliably look at these and use these in quantum simulations that I want to run. Because sometimes it was almost nothing that would change, or the T1 time would change by 1 microsecond, or the temperature by 1 millikelvin or something, but sometimes it was more significant. And the temperature would be 20 millikelvin instead of 15 or something. And depending on how accurate you want to be in your quantum simulation, it's a good thing to know. We also noticed that when, yes.
Yeah, that's not so you're estimating like first what the actual parameters are, and is there like a variance between if you do the same experiment on different days?
Yes, what we did to find a variance or confidence was to not just run every time from the same set of calibration data and then down to the optimum solution, but have the original set of calibration data and then add noise to it through just a Gaussian distribution, do 100 iterations of that, and then find a margin of error for how many times or how it decays. But the idea also then was that going day to day, that you don't have to rely on the recalibration data from the back end, but you can run this simple loop and it'll give you the actual parameters that'll fit how the system is behaving right then, or at least for the time frame that you're working in.
Because yeah, they update those parameters every day, like they recalibrate them for this day, but it's just something they calculate at the beginning, either like that.
They calculate it, or they recalibrate it, or post the calibration data about once every hour, sometimes once every 2 hours. Yeah, but then if you doing a very sensitive, parameter sensitive experiment that's at the end of the calibration data or somewhere in the middle, and you think, okay, these data were taken half an hour ago, I don't really know if the system changed or not, but there's a way to do it directly before and then do your experiments directly after, so it's as close as you can get. And then it doesn't rely on them just fitting a simple exponential curve to get a parameter, but rather the full spectrum comprehensive parameter extraction.
But the user team first have to like get all of that data, right?
And then you put the code and then you have the parameters.
Yes, so it's not an instant 2-second process, but it is if you want to be sure that you are calibrating it much more accurately than you could have if you want to wait another half an hour to get the calibration parameters from the back end, then this is a way to do that.
But I would also imagine maybe you could just program this in as something that happens at the beginning and the end of your experiment.
You could.
can like update based on the result. I mean, you can do everything as one experiment.
Yes.
But then the post-processing, extract the calibration.
Yeah, so it's much more customizing it kind of to your exact time frame that you're working in and on the circuits that you're working on and in your training loop. So you can set, like you said, the calibration data as part of your experiments, as part of that set of series of circuits in one job. But then also it will work much better if it's not just on the pre-IBM Quantum computers where you have to sit in the queue and they might get interruptions to that. But if you are working with an in-house quantum computer, then it's a nice, convenient, and easy way to run as many circuits as you want, as many series, as many repetitions of this as you want to fully just know what the quantum computer is doing. Because even with the temperature, you might be able to control the temperature through your dilution fridge, but that's not going to necessarily give you the exact temperature that the qubits are at.
So I don't understand, right? But like the point of this is to find out some specific hardware parameter demonstrated for to verify other experiments, right?
Yes.
Right. So I actually I have a question. This is quite a silly simple question. But how constant are these hardware parameters, right? Like do they vary with experiments or like conditions? Like to what degree can you do this one experiment and keep this, like the same hardware parameters for the following experiments?
It depends a little bit on the which parameter it is. Like usually the qubit frequency is kept very constant, that almost never changes. The T1 time might change by less than 10 microseconds if you're lucky, but sometimes you get unlucky and based on previous circuits or how they reset it or any other noise that comes into the system, it could fluctuate by quite a lot. Like we noticed a few times where I would look at the calibration data and it would say the T1 time was something like 150 microseconds. And then when I would measure it, then it would suddenly be just 100 microseconds or it would go up to 250 microseconds. But then when looking at it, doing a few experiments in a row, it would stay constant during that time frame that I was using it for the handful of circuits that I sent one after another, or even within 10 minutes of doing it, that they stay constant within that, but I couldn't rely on the data from an hour ago. So it's as close as we could get to having an immediate calibration right before your experiment.
Okay, that makes sense, right? What we're very like sensitive to external variations.
Yes.
So that would include basic apply for if you want.
Yeah. But yeah, this also did show that the IBM quantum computers are very reliable. It just depends how specific you want to get. If you really want to know down to the exact microsecond what your T1 time is, then you can use this. But in general, for all intents and purposes or of general use, the IBM quantum computers are very, very reliable with keeping their systems noise-free and Markovian and reliable and useful.
So you have your own quantum computer. How long does this process take?
The full loop, the longest part of this was the actual sitting in the queue and waiting for the experiments to be run, but each circuit only takes a few microseconds. So doing that takes probably less than a second for the full actual circuits to be run. Yes, to get all the experimental data. And then for the optimization loop, that was also, it was a bit slow in Python. It might be made faster in something else like Julia. But we had to use JAX for a just-in-time compiler. So it took maybe 20 seconds for the first loop for it to solve the equation the first time for it to compile. And then for the full then iteration loop, depending on how much you want, what kind of convergence criteria you have. I think it would take about either between 1 minute to 5 minutes to do the full calibration. But then that gives you data that is very reliable for at least like the next half an hour to an hour, depending on how fluctuating your system is. But yeah, so it's almost ideally would be that IBM could take this and replace their calibration methodology with this, and it would be interchangeable. Just a more reliable version with this because it does everything comprehensively. And yeah, they could then do it more regularly and give actual more up-to-date data every 5 minutes, every 10 minutes. Yeah, so it's not instant, but it is quick enough. It's better than waiting an hour. That we also noticed a nice bit of consistency with the circuits in that we could look at 2 qubit pairs and a 3 qubit triplet and look at qubits 0 and 1 and 1 and 2 and see the coupling constants between those and the coupling constants between those. And then look at the 3 qubit system of qubits 0, 1, and 2 and see that it doesn't make any difference if you use the 3 qubit system or 2 qubit systems. Because then if you want to look at scaling that up, if you want to look at, like now the quantum computers are like 150 qubits, to solve the GKSL master equation for 150 qubits, you'd have a 2 to the 150 size matrix, which you can't really solve in any meaningful way. But you can do a series of 2 qubit circuits that are just stitched together. So instead of having to do tomography on the full device all at once in this way, you can do it on just the 2 qubit pairs, and it's very consistent among those, which makes it also much more computationally efficient because you don't have to do full quantum process tomography on your whole device. You can do it qubit pair by qubit pair.
So yeah, that kind of relates to what I wanted to ask before. Was there any like control operations? It was just ROI gates. It wasn't like a controlled ROI.
It was just the single qubit gates.
Yeah, I'm wondering with a like gate that introduces entanglement, not maybe make it more non-Markovian or like have be different than this.
It would probably have at least some kind of a effect, but we weren't really sure exactly how to go about looking at modeling that just yet, because we wanted to look just at the more simple benchmarking circuits, but then also to see it would be a little bit difficult to really know what's going on then if you have 2 qubit entangling gates, then to find is that really Markovian or is that non-Markovian. The line gets a bit more blurred there because then it's on purpose that there's information being shared between 2 qubits and not accidental energy leaking into one of the other ones.
Yeah, but do you like just if you think would it be that if you have an entangling gate, there's a higher chance for like it's more expensive operation than like just a single qubit gate on the implementation side, and then maybe that would cause like that photon thing being absorbed by another qubit that it shouldn't have. Like, is that a concern or is it not like a thing?
It could possibly be, but I think that the systems are, based on what we've seen of like how well behaved they are, I think for their 2 qubit gates, they probably follow a similar trend. There is one circuit that I did with the entangling gate, just to test, but I'll show that later, but I'm not sure if that's really the best example, but it would be interesting to look at how that scales with 2 qubit gates. But I think it would work still quite well. But yeah, that would be interesting follow-up research. Yeah, so we looked then for 1 qubit, the results that we got were very clear. We got very definite T1 times for all of them. Then looking at the 2 qubit pairs, we found the exact same T1 times for all of those qubits. And then it's only from 2 qubits and upwards that you have coupling constants, because then that's the only time that they actually can couple. You can't couple 1 qubit to itself. And then looking at the 3 qubit system, the performance scales just as well. It converges very well and finds graphs just as well. It doesn't struggle at 3 qubits. 4 qubits it probably will, but it's also then unnecessary because, like we've shown that, and we show in the paper that using just 2 qubits and stitching them together gives you all you really need. You don't have to go bigger than that. And what we wanted to also do from here, as suggested by one of the reviewers, was to look not just at its ability of then fitting its own data and finding those parameters, but then seeing if you can find perfect parameters from a T1 system, and through the optimization, it fits perfectly your T1 circuit, but then it is completely useless for any other circuits, then there's no point in doing it. So we wanted to look at the predictive ability. And this is where, just for demonstration here, I mentioned that there's the unoptimized results and then optimized in the thick line, where you can see that it's the same shape, but just tweaking the parameters makes it fit actually much better. So it is, we could see, as far as we're concerned, it is Markovian, and then we can optimize and tweak the parameters to find an exact fit rather than a pretty good fit. And from here, what we did was we did the T2 version of the experiments to then find the T1 time, the both of those on 2 qubits. Then you have the frequencies, the T1 time, the T2 time, the qubit coupling, the temperature, all of that, and use those parameters then to solve GKSL equation for, say, a Bell state. If you put it into a Bell state of just a Hadamard and a C0, and then let that go through decoherence and relaxation, then how does that compare to using the methodology of taking the experimental data and then using the claimed hardware calibration parameters? And we saw that the optimized data that we got from the T2 circuit fits better to the Bell state version than the hardware calibration that IBM provided. So it can predict your systems very well. So you can use it to run these 2 or 3 benchmark circuits of T1, T2, and T2 star, and then know confidently that that will fit all other circuits that you might run or try and solve using those hardware parameters, which is a very encouraging result to see, and quite nice to see that it works better than I even expected. But yeah, so that's also the tricky bit when looking then at the C0 gate, because all of that puts it into a certain state, and then you see where does decay from there, or where does it decay in between 2 gates. If you have a very deep circuit, how does the decay happen throughout the circuit? That would be harder to look at because you need to construct the circuit in such a way that you can have a peak halfway through the gates or something. But it was very promising that it still seemed to work well, even with 2 qubit gate thrown in.
Yeah.
It would,
It's like maximum tangle, so that's a nice indication. Right.
yeah, which is a nice way also to show that it probably will scale it. We know that these are also very shallow circuits, very basic benchmarking circuits of just like a T1 is just the X gate. The Bell state is also very simple. It's not a very deep circuit, so it's not going to be directly applicable then to something like making a variational circuit or quantum convolutional neural networks, anything like that. It might get a bit too deep and a bit too noisy there. And in states like that, it might be where the non-Markovianity comes into play, where it's just because there's so much going on that it might start to become non-Markovian. But in those cases, then we can look at the papers that we found in the research where they mention, okay, this system is non-Markovian, this is how to deal with it. There are other frameworks for how to deal with that, but that's beyond what we wanted to do here. And yeah, that's mostly the presentation. If you have any questions, I'll be able to answer them. If you want to go to the paper, there's scan something there, but yeah, that's.
So for quantum devices, we choose different devices.
Yes, originally it was focused just on the Markovian modeling and parameter extraction for IBM quantum computers, but
I know, but
there's
they
nothing.
have different parts.
Yes, but there's nothing special about this that's only applicable to IBM computers or only applicable to superconducting plasma qubits. Any gate-based quantum computer this can be used for, because it is just the gate-based circuits and then open quantum systems master equation that you're applying. You could apply it to any other gate-based quantum computer hardware. I think so. There's no reason why it shouldn't work, but we didn't look on the other ones. But yeah, as far as we know, it should work. It's a hardware-agnostic framework.
Has anyone ever done this comparing different platforms?
Not that we know of.
Or doing that after each recalibration, seeing how much of a fluctuation with the E1 to the star state or some statistics about that to see how stable it is.
That would be interesting to look at, but we didn't see anything like that in any literature anyway. It was quite a big gap on this topic that no one had really written anything about it. Like, that's why I say that even the only actual research that we found was talking about that assumption. Okay, there's already non-Markovian frameworks on how to deal with it. But even from the back-end sides, there's no actual research that showed fully that they are Markovian systems and that they can be modeled this way. It's only hinted that way. Like in the Google famous quantum supremacy paper, then they talk about models that they use and apply to it that kind of goes through the assumption that it is Markovian, and they talk about the locality of the models that they're using. And yeah, it's also, they kind of use it as a foregone conclusion that is Markovian, but there's no actual research of looking at it and showing this is how it works. So you thought this filled that gap. And then with any other hardware, same thing, that there's not real much research. It's more just something that they found kind of worked for them and kept internally, I guess. But he has a good framework to test on all sorts of hardware. It'd be nice follow-up research.
Probably put your life in danger.
Maybe not sure how many secrets I'm stumbling upon with this, but I think it should be fine. No one's come after me yet. It's been a couple of years. Yeah.
It's the longest you ever waited. I'm just a great.
I think one of them I had to wait something like 3 days. But that was still when it was like in its infancy, and I was still using the tiny little computers of, for some of them I had to use the 1 qubit device back when that still existed just to get some data. But a lot of the time I saw the queues were up to a month, and I just didn't want to even put up with that. So I wrote parts of the paper and waited to come back to my experiments once I could. But yeah, the queues were very, very bad, and I imagine that it's maybe even worse now. Yeah, and that's also the downside that we found, was that everywhere we look, only Qiskit and IBM Quantum computers allow you to actually make this delay gate. We just tell the computer to do nothing and let noise relax the state. Penny Lane doesn't do it, Cirq doesn't do it. No other platform or framework does it, only Qiskit. So we were very much stuck in using this, but technically you can implement it on any computer. It was just much, much more difficult than we anticipated to, yeah, spread that across frameworks.
Ask a few questions?
Yeah, of course.
So with the fitting and the model that you're using,
Mhm.
you assume that the parameters between the two qubits can vary independently, so you don't fix them. So like, for example, the decay rate and the qubit frequency, you allow it to vary.
Yes.
Between the two qubits. Is there like a significant variation that you can find in the optimization? Or?
Not very significant. Usually we found that the biggest difference between them would already be in what the parameters were. Like sometimes 1 qubit would have a decay time or a T1 time of 150 microseconds, the other one would have like 175.
Yeah.
But then when we optimize them, then they would only tweak slightly to be then 172 and then 176 or something. So the variation between them was much, much smaller than the initial difference between two qubits, but they were all allowed to vary independently. Also, what we found in the paper was, I mentioned earlier, instead of using just the single parameter coupling constant, we used the full coupling constant matrix to see if there's any other degrees of freedom that they might be coupling to. We found that there's nothing really that they couple to outside of the one that you want, which is just directly between each other, which is a nice thing to verify, but it's, couldn't just go as an assumption because you don't know if there's anything weird going on unless you look, and we found that it did.
Yeah. Did you also benchmark your results against, because they had the simplified model, did you also apply your fitting to that one and see if there's any big difference? Like, did you benchmark your results with the full X, Y, Z interactions against just the normal, like sigma plus and minus model? If that makes sense.
Yes, and that's where we found that there wasn't really much of a benefit of including the full bigger matrix, but their simple model does work.
So most of the results you had was just the same model that they used, but with optimized.
These were with the bigger model, but when comparing those, we found there was almost no difference. But we thought, okay, just better to be better more data than less. So we used the bigger model, but we found that there's almost no difference.
I don't know how the IBM devices actually works. I imagine like the J matrix basically models crosstalk between the qubits.
It can be, yeah.
What interaction? So like I was thinking, like, sure, it depends on, say for example, you put in a request to run 2 qubits. How does the device actually choose what qubits that you're using? Because imagine if you have qubits that are, for example, in different locations on the circuit, the crosstalk would be different depending on when you run it. So that I don't know.
Yes, that's in all of the examples that IBM gives of this is how we calculate T1. Not only do they fit the simplified model, but they also choose qubits that are split by some neighbors, like they have 1 or 2 other qubits in between them, so there isn't any risk of crosstalk or much less. And that's also what we wanted to look at, to see if there are 2 right next to each other, would they then influence each other when they're not intended to? Like if they run independently circuits of just a T1 circuit of a simple excitation run on each independently, they shouldn't communicate. But if they do, then we'll see it this way. That's also why we wanted to look at neighboring ones, rather than just seeing ones on other sides of the device.
Qubits to run.
Yes.
Okay.
And that's also what we wanted to see then. That's with the linear model that I showed, where it's just 5 in a row. We can see if one is in the middle and has 2 neighbors and then 2 more neighbors on the side. Does that go through any more changes than one right on the edge where it's far away, far removed from everything? But we saw that everywhere it's very consistently, reliably Markovian system.
Okay.
at least for these benchmark systems, but I know that there are still a lot of papers on crosstalk in these devices and non-Markovian models to deal with problems that you might have, that it might get bigger and worse with deeper circuits, but at least for the benchmarks that you're getting, yeah, they're trustworthy.
Yeah. So I'm also thinking about so you use the Markovian master coding to model both the 2 and the 3 qubit case. Because I would imagine that for the 1 qubit, maybe I missed this but in the 1 qubit case, it would be Markovian if you had interactions between the other qubits, right? So if your J matrix basically had interactions, the single qubit would be Markovian solution. Because I'm thinking back to like the talk last year with the guy from NPL gave, and what they did was they showed like 3 different models to look at like a single qubit, and I think I'm trying to remember now, like they used a post-Markovian master equation, which is able to capture to a certain extent some non-Markovian behavior, and then they had the 4K based post-Markovian master equation. And they also used another model which was basically a Markovian master equation, but they added an extra qubit in to like model the non-Markovian crosstalk. And basically they found that model was like really good at predicting like the single qubit behavior. So I was thinking like your model seems to be similar to that. Like basically you like at the level of 2 qubits it's Markovian, but if you look at a single qubit, right, it would be non-Markovian.
No, I think at a single qubit it's still Markovian, because then you can even look at the 3 qubit system, which is just 1 qubit in between 2 other qubits. They're all still single qubits, they're not interacting. But
I would have thought it would change the more qubits added or took away.
Because they're not supposed to be interacting with each other anyway. They're all independent circuits and operations. It's only single qubit gates. But if there is then any kind of interaction, then we'll see it as a non-Markovian influence, because it's not meant to be there.
Yeah. But I mean, even if you have crosstalk between 2 qubits, you could still use the GPSL master gradient for the 2 qubits, as long as there's no other significant crosstalk between those 2 qubits and the other ones. So that's basically what I think the people at the NPL did, is they modeled this crosstalk by just adding an extra qubit to their model, and they found that this gave like a good prediction of what they were seeing on the other bit. I'll have to read it at the paper again. But
Yeah, it sounds quite interesting. I just want to.
and I'm trying to also remember the protocol that they used, because they had this kind of. What they did was that they applied these gates, but they applied 1 gate and then kind of applied the reverse of that gate, and somehow it had like it was like some other type of protocol that they used, but they were looking at a similar type of setup of how you can. They were more interested in modeling that in non-Markovian perspectives, but I need to read it for that paper again. But I think yeah, there's crossover between what they were doing, which we were doing as well.
Yeah, it could be, because we know that also this was a very simplified model, and there definitely is presence of bigger things of non-Markovianity and crosstalk, but that's other papers already covered that. This was looking at just the step 0 of all of that. It was an uncovered topic.
Yeah, I think that's the questions that I